last presentation before lunch. And since I did give a similar presentation to another IEEE event not too long ago, so if you have seen most of the slides, I apologize for that. I only have this many tricks to play. I have to decline it. So I'm here to talk about something more boring. I guess less boring than legal, but more boring than taking pictures. Safety with flying UAVs. I'm going to only touch one aspect of that, which is how to maintain safety of UAVs flying in an environment where you don't necessarily always have GPS. So first, I'm going over some background on why GPS is important for the safety of UAVs, and then talk about what we can do without it. So safety. Of course, we start with something extremely unsafe. Do not repeat at home. So this is a little UAV that we set to fly in automatic mode. And this is about 2 summers ago. So this little UAV right now is navigating inside a building. This is one of our labs. And what we're trying to demonstrate is how the UAV senses the environment and how it seizes me, and how to dodge from me and some other objects randomly placed in the room. And of course, we heavily modified this little UAV, which is a 3DR quad, to be able to do that. And even that, we don't feel like it's safe for anybody to try. So anytime you see me playing video like that, it's always going to be me in the video instead of the student. So, was that flight safe? Well, we did modify some of the subsystems to make it safe. Usually, this is what it takes to fly UAVs in automatic mode safely. So you need an autopilot system with navigation capabilities. From that, you need to determine the orientation or attitude of the heading with GPS and another sensor called inertial measurement unit. With those two, you can then do flight control and path planning. So you don't necessarily have to control every move of your UAV. Where you have a good navigation control system, you can basically just pinpoint 2 points on a map, and your UAV can go from point A to point B, no problem. That's path planning. So next is something that you don't always have in today's UAVs. We will have to have a sense and avoid system. A lot of the aircraft, especially the military ones, will have that, so that the UAV can see what's around it and to avoid what should have been there. And on top of that, you have the functionalities that you fly UAVs for, such as taking pictures or mapping. So all those subsystems were actually enabled by GPS in today's technology. Whether or not we realize that, it is actually the core technology there. It makes our life easy. However, we have to understand first why we need that for the safety of UAVs. What is GPS really good at in helping with the safety? The GPS gives you accuracy, so you know your location pretty accurately. It gives you availability. So most of the time when you need it, almost most of the time when you need it, you turn on the UAV, it knows where it is. It has continuity. Once you start a trip, unless you're traveling through heavy woods or traveling through buildings, it's always going to be there throughout the whole trip. Well, of course, again, unless someone is trying to jam you and try to bring down the UAV. And integrity. So usually when GPS or a good GPS receiver reports a position, it knows its own position and is sure about it. Now, whether or not you can be sure about your position out of GPS is a critical safety issue. You do not want to be overconfident on your position solution. Example, we just saw UAV flying, taking pictures, maybe getting close to houses and buildings. Now, if you're not really sure about your position and you're not aware of that, you may be crashing into the building if you're off course by a little bit. On top of that, GPS provides a low cost, size and weight solution and low power. And GPS is usually pretty fast. There's not too much complicated processing inside the GPS receiver. So GPS can report position and velocity in real time with a relatively low latency. So what makes it so good? You have the satellites, you have the signal from them, you have your ground antenna and receiver, all combined together will allow you to use passive receivers. So your GPS receiver doesn't need to talk back to the satellites and gives you global coverage. It also gives you redundancy. In addition to all the satellites we have in GPS, you have other GPS-like satellite systems, and we call those GNSS. They're essentially copies of GPS run by other countries. And you combine GPS with what we call the inertial measurement unit. Both will be used to provide real-time high-rate data in the control loop of UAVs. Now, when does GPS become less reliable? Well, GPS will not work because A, you're trying to fly in buildings or through a city where you have blockage, or you're trying to fly it under treetops, or you're trying to fly it where people could intentionally or unintentionally jam the GPS. Or sometimes in certain parts in the world, you have strong effects happening in the atmosphere, especially in our ionosphere. That will also destroy GPS performance. And of course, a lot of times you're not completely blocked, but your GPS receiver will be seeing signals reflected from ground and surface of structures that will create extra large position errors. In all these cases, GPS may not work as well as it should have been. And today's talk, we're going to focus on one very hot area, which is how to operate a GPS through buildings and cities. In that case, blockage is our main enemy. So with GPS, as I explained before, you can send high-rate position, velocity, and orientation data to other parts or other subsystems of your UAV. So your UAV control, sense and void, mapping, and a lot of other functions actually are dependent on the high-rate data coming from the GPS inertial combo. In an urban area or indoor environment, you don't have GPS anymore. Therefore, your high-rate data feed into other subsystems are no longer there. Now, in that case, we cannot guarantee the safety of these UAVs anymore. Now, how do we deal with that? So, the goal here is to achieve GPS-like performance, accuracy and robustness-wise, without using GPS. In particular, we need real-time position and velocity fixes. Now on the right, I have a picture, and some of my friends in the Air Force refer to that picture as the redneck version of sensor package. So you have wires flying around, and you have actually a lot of expensive equipment on there. I have a vision band camera, a infrared camera, some other small cameras, GPS, reference GPS, laser scanners. This is the best you can do when you only have one undergraduate student working on this on part-time. So the keyword here is we are going to have to use other sensors. Now, if you're dealing with a large vehicle or a military system, sometimes you have the luxury of saying, well, in order to work with GPS, I am going to order these sensors, and they are going to be on my UAV and I will be able to fly them. Now that's not true for small vehicles, even small military vehicles. Oftentimes you have to get away, we have to try to get away by sharing other sensors from other systems. The most commonly used one is camera, and in our research, laser scanner too. So in order to achieve GPS-like performance, we cannot use the GPS navigation algorithm, obviously. What we'll have to do is we'll have to implement some other navigation estimation algorithms. Two commonly used ones, one is called the SLAM, Simultaneous Localization Mapping. So you can actually navigate to a map that you're estimating on the fly. The other type is odometry. It's not that different from your wheel odometry, where you know how fast you're going. Instead of using wheels, because you're flying, we'll use other sensors to measure that. Now, so when you do everything properly, even with cheap parts, you will be able to have this little UAV navigate inside a building. And once again, that's me in front of it, not the student, just to be sure. And you will be able to navigate through the indoor environment safely. In this case, we only used low-cost camera sonar combination. But that was done in a very well-controlled environment. I may have to restart the video, I apologize for that. The example you just saw was done in a very well-controlled environment. Do I want to put a UAV in any room where there are a lot of people walking around and still guarantee the safety of it? No. That was just a benchmark test. Now, in general, we're looking at other sensors to help navigate the UAV. And the first one is, as I mentioned a couple of times now, the inertial measurement unit. Now, traditionally, inertial measurement unit comes in a bulky box, like this guy here on the left, on your left, which is about a box of this size, and that gives you very good performance. Now, with ever-evolving technology in the industry, we are able to bring it down to a lot smaller size. So you have chip-size version of these things. But the problem is the low-cost ones typically drift very fast over time. So the unit will measure velocity and orientation for you, but that's only going to be good for the matter of seconds or minutes. So in other words, you cannot rely on this sensor alone to fly your UAVs. So in addition to that, we can use laser scanners to help with the system. Now, like I mentioned before, for small UAV systems, you want to reuse the same sensor for different subsystems. Now, for the lasers, we use lasers to scan the environment, and we use lasers to build 3D maps, and we use lasers for sense and void. And we can also use lasers to navigate. Here is what a laser sees when a UAV is traveling inside the room. So we have a large lab space set up with a few corners in there, and the little UAV laser is traveling through the room and sees all different objects. And most of them are walls and surfaces that will show up as a straight line in the UAV data. So how do we navigate to that? There are two ways. And the method I'm going to introduce today is to navigate measure the displacement and rotation in real time. So what happens is when you see a fixed object like a wall, it will show up as a line in your laser scan. And from time to time, you will see that your distance to that line changes. Of course, that line doesn't move, it's from a wall. So the distance change reflects the velocity of the UAV. Now by comparing laser scans between two scans or two frames, you can actually deduce your own velocity or motion in two-dimensional space. Now that is an older technology. A newer technology that we are recently discussing is to do three-dimensional displacement measurement. So if I have two lasers, I scan a wall surface, I'm going to get two lines. From these two lines, I can mathematically determine the equation of this planar surface. And then I can find out the 3D motion, and including displacement and rotation relative to this wall. And from that, I can solve for the UAV motion. Now, that all sounds nice, and it's actually not that hard to do in real time either. So what's the big challenge here? Safety issues. Now, if you actually try to fly that thing in a room like this, most of the time it will do well. But once in a while, you have people like me walking around, and you have moving objects. When you have objects moving in the laser scan, and your laser is trying to navigate to that moving object, we're going to have a bias in the motion estimation. Okay, if you don't take out this bias, it's going to cause a stability issue with the vehicle control. For example, if you're moving in front of a UAV, and the UAV will get a wrong estimation of its current velocity, what will happen is the flight control is going to try to compensate for that velocity in a wrong way. And of course, and that will also cause you a bias in the understanding of other sensor data. All these combined could actually lead your UAV to go haywire, and we have seen that in real life too. So as far as safety is concerned, we have to make sure that we can trust the laser data. So for that, what we're doing is we're developing an outlier detection algorithm that will detect and exclude any moving objects. So we have demonstrated that in a small room or hallway like this, even when you have people and people moving around, the door opening and closing, with two lasers scanning the environment, we can actually measure velocity pretty reliably, and we can actually detect whenever the thing's moving and exclude those. So you can do something very similar with cameras too. And cameras are more often used in almost any UAVs you have today, more popular than lasers. So how can we do the same thing with cameras? So first we realize that camera images are two-dimensional. So as the cameras are used to collect other data for like photography, we can also recognize and track point features in the camera images. And then we can try to locate the 3D location of those point features and navigate to a map of these point features or landmarks. So if you look at a simplified camera model, you have one object in 3D world, and it's going to be mapped onto a 2D image in your camera CCD or CMOS. Now if you know the location of the 3D object, and if you know where you saw the object in your image, you can actually back out your camera location and orientation relative to that object. Another method we use is called epipolar geometry. If you actually see the same object from two images, that will give you a constraint on the rotation and displacement of the camera between these two images. Both principles combined will give us a way to navigate using cameras. But yes, we have the similar concern with safety here. It's all nice and done, and it's been a textbook for years. Why is it people are still not using it to fly UAVs through buildings? One of the biggest challenges we have is incorrect association of images, maps, and features. So what happens is, if you are taking a picture of this room, for example, you have all these chairs. They pretty much look identical. If I'm navigating to one of the chairs, How do I make sure that I'm always tracking the same chair from frame to frame? If I'm jumping all over the room to look for the wrong chair association, my position and velocity estimation will again go haywire, and that will crash my UAV in a matter of seconds. And that's one of the biggest challenges why we are not flying UAVs with cameras and lasers today. How do we make sure that we can trust these cameras for navigation purposes? Of course, we have to do outlier detection to exclude wrong associations. Another common problem we found with cameras is that it tends to be overconfident about its estimation. In other words, when I see 100 chairs in this room, and I think I measured 100 different independent measurements, and I think that gives me a very accurate position and velocity. Well, in reality, I may be only matching 90% of them correctly. Another 10% may be matched incorrectly, and I wasn't aware of that. So I'm going to be overconfident about my estimation. In that case, I'm going to tell my flight control that I know exactly how fast I'm moving and where I am. Where in the reality, I have a bias in the estimation, and that will destroy your flight control very, very quickly. So the two items that we're working on right now is to build a more robust outlier detection and build a more conservative modeling of uncertainties so that we know when we are wrong. So we have been able to demonstrate how the camera system works with a fairly small camera with a low-cost inertial measurement unit. Here we have a sensor setup. It's actually not flying, but on a cart on the campus of East Carolina University. And as the ground track moves along here, as you can see the green, we are building a map surrounding ourselves, and it's calculating its own position around this great circle here without using GPS, and that will be used to replace GPS. And of course, you are navigating to the map. There's a bunch of small black crosses here. You're navigating to the map you're building when you're on the go. So as I mentioned, we have the outlier detection issue that damages the integrity of our navigation system, which is one of the biggest challenges for safety of UAVs today. If we have unlimited power and computation resources, a lot of these can be solved. However, we don't. When you're flying on a small UAV, you typically have a credit card-sized computer. Those things do get faster nowadays, but still, you cannot throw in any algorithm you can find in papers and hope it'll work. You have to optimize it for low power consumption and fast computation, low latency estimation. I'll give you an example. So if I have an estimation algorithm using lasers and cameras, and it will be 100% accurate, but it has to wait 1 minute to get a result. It pretty much does exactly nothing to help with my flight control. Things have to happen within a second for the flight control to react. And we have a little bit of observability issue. For example, you are scanning a 3D world with a 2D laser scanner or 2D imagery. We have to recover 3D position from 2D. That's less of an issue compared to safety caused by outliers and constraints on the resources. So I actually just scratched the surface of a few projects we're currently working on. We want to thank AFOSR for sponsoring part of the projects, and the Air Force Institute of Technology, Institute of Navigation to pay. I thank them for paying for some of our student research projects and NC Space Grant. Finally, before you go to lunch, any questions you want to ask PD?
I've worked with low-level flight, fixed-wing flight a lot, and I know the huge problems is power lines and antennas that are shorter than 100 feet.
Yes.
Is there any program going on to get the FAA to extend their database to cover such things for UAV.
I'm not aware of anything for the UAV, but for helicopters, there was something going on. I've been out of the industry for 3 years, so I can't tell you any up-to-date development on that. But for a while, we realized that the power lines especially is going to be a huge issue for small UAVs, especially in automatic flight mode where you don't have the first-person view. The potential solution we were talking about at the time was to use infrared cameras, but they're expensive, and the small UAVs can't afford them. So, but if you do have infrared cameras, there is a method we've developed that can locate where the power lines are in the 3D world. You not only know where it is in your image, you actually know the 3D position of that. That will really help you with your flight plan. So, yes, we know it's an issue. No, there's not a good solution to that, but we have a path forward. Yeah. Thank you, sir.
In the discussion, the model is overconfident when it's looking at 100 chairs as landmarks and things that knows where they are. Is that because it treats them as independent when they aren't really? That because if it has 100 landmarks and it says, okay, I see this one that agrees, and this one agrees, and this one agrees, and it does it 100 times, and it says, I'm 10 to the 99, confident. When it's really independent landmarks, is that?
So there are two reasons causing the overconfidence problem. And what you mentioned is one of them. It's a big one. So when you see 100 chairs in here, they are not all statistically independent from each other. If you don't take that into consideration, you think you just got updated 100 times using an independent source. Since we are updating 100 times with a noisy measurement, we are sure that we can reduce the noise by 100 times, the variance by 100 times. Well, in reality, that's not true, because a lot of errors you see in these 100 chairs will be correlated with each other. And that will cause your measurement to go overconfident. Now, there are solutions to that problem, and that's a huge problem, but it's slightly easier to deal with than the problem of mismatch. So if I have 100 of these chairs, 10% of them are mismatched, and I didn't know that, I will be 99.669% sure that I'm here. In fact, you're not. Your 10% measurement is even like way off. So we are dealing with both issues. Overconfidence due to repeated measurements and overconfidence due to incorrect association. And this is not just UAV industry, this is big in robotic vision. How do you get consistent, the word they use is consistent. How do you get consistent estimation out of vision-aided navigation systems? Thank you. Yes?
How do you deal with like mirrors or reflective objects? How do you deal with mirrors or objects that have reflection on them?
In cameras or lasers?
Camera, for both.
For
So,
both.
Because the laser would detect this on there, but the camera wouldn't see that. Something
Okay. So if you don't have anything special done to the hardware, so in other words, if you already have the mirrors in your view and there's no way to get rid of that data, the only protection you have against that will be your outlier detection. So if you're flying in a room with all ceilings and floors and walls made of mirrors, then you're screwed either way. Okay? But if you fly in a room that you have only one window in front of you and the rest of them is just regular features you can see with laser and camera, or camera, you will be able to detect that mirror as an outlier and exclude it if that mirror is not going to agree with the rest of your measurements. The problem comes in, especially with a laser, that you are scanning in an environment where you have 2-3 features you can see, and one of them is a bad one. And there you don't have the capability of necessarily throwing out the outlier. But at least we should know that we are not certain of the measurement. If I'm not certain, then I may just let UAV fly and coast, what we call the coast through that period, without using the laser or camera updates. If we can't trust it, we don't use it. Thank you. Okay, looks like everybody's ready for lunch. Oh, sorry, one more. Yeah.
Just a quick question, kind of following up on. So, I'm not very familiar with computer vision, but isn't there something where you can say the more unique something is, the more weightage I will put on that because I'm unlikely to mistake it for something else?
Yes, there is. So for point features, when you match, say, these chairs, their descriptor may not be that strong. So when you match them, you actually know how well you match them. And in that case, you may be able to choose only the good ones to use for navigate. The problem with that is that approach typically takes a lot more computation power than the approach without it. So a lot of times people just don't use that for certain types of estimators. Even when this happens, even when we do have the quality of these feature points, in real life, in real world application, it's not a good enough guarantee. So it's one level of protection we'll use. We'll use anything we have, but that's not going to be the only level we can rely on. You have to add on other layers to make it safe. So it's some information we'll use if it's available, but we're not going to be 100% relying on that. Thank you. Well, if you have any more questions, I'm going to stay around for free lunch. Thank you very much.